Hi, this is Lisa McPherson with A Plus College Ready. Today I'm going to go over the solutions to the practice problems for Unit 4 with you. So let's get started. Each one of the problems, and there are 30 problems, all multiple choice. These problems, I will have 2 slides for each problem. The first one will have the question, and also it will have the correct answer. And you can see the correct answer will be marked in red. And then the second slide will have the answer and a brief summary of why the correct answer is correct and possibly also why the other choices are incorrect. So let's start with question number 1. The elements in which of the following have most nearly the same atomic radius? So clearly A is the correct answer, but why? Well, beryllium, boron, carbon, and nitrogen are in the same period, so they have the same number of energy levels, or energy shells. And that means that their radii aren't going to change a whole lot compared to elements that are in different periods. The other choices, B, C, and D, show elements that are in different periods, and as you go down the periodic table through groups or even diagonally, you're going to be adding energy shells, energy levels, and that's going to make the atom or the atomic radius large very quickly. Excuse me. Number 2, which of the following represents the ground state electron configuration for the manganese 3 plus ion? A is the correct answer because you can see here, if we take a look at the manganese atom in its neutral state, it has an electron configuration that ends in 4s2 3d5. I've put the 4s2 after the 3d5 just so you can see that that's the highest energy level farthest from the nucleus, and that's where our valence electrons will be. When creating cations, we're going to remove those valence electrons first, and then the next most highest energy level electrons following. In this case, we're going to have to take both of those 4s electrons off, and then we'll need to take one more from the 3d, and that's what gives us the correct answer. All of the following statements concerning the characteristics of the halogens are true, except. Wow, love these types of questions. Not, because these questions, they're saying, hey, everything here is true, and you're looking for the one thing that isn't. So they're sometimes a little bit more confusing. So you really have to take your time in analyzing what's happening here. Turns out C is the correct answer. Why? Well, A, B, and D are all true statements. The first ionization energy, they decrease as atomic numbers of the halogens increase. They're saying down the group, first ionization energies actually do decrease. You can just memorize the trend, or if it makes sense, we're adding energy levels, and therefore the electrons are getting farther from the nucleus. Increasing distance makes electrons easier to remove. That will decrease your ionization energies. Fluorine atoms do have the smallest nuclei because they have the fewest number of energy levels. And D, fluorine is the most electronegative of the halogens. It's the most electronegative of all elements. So A, B, and D are true. So why is C not true? Well, as we know from reactivity trend, that for nonmetals going down a group, reactivity decreases. Remember also back when we looked at types of reactions in your pre-AP course, the activity series for the nonmetals and particularly for the halogens, what we discussed was that iodine is lower in the group and therefore is less reactive and will not place bromine in a chemical reaction. So that's why C is our correct answer. Number 4. In which of the following groups are the 3 species isoelectronic? So we need to remember what isoelectronic is first. Isoelectronic simply means that the atoms or ions in the list will have the same number of electrons, and therefore the same electron configuration in their ground state. Why A? Well, when we look at sulfur, potassium, and calcium, let's first take a look at the numbers of electrons that these atoms have in their neutral states, and then correct for the charge. For anions, we have to add electrons. So here when we add the 2 for sulfur, we end up with 18 electrons. For potassium and calcium, though, these are cations. We're going to have to remove electrons, so we're going to subtract whatever the charge is and end up with 18 also. Number 5. The effective nuclear charge experienced by the outermost electron of sodium is different than the effective nuclear charge experienced by the outermost electron of neon. This difference best accounts for which of the following? Let's go back to that initial statement. They tell us that their effective nuclear charge, or ZEF, is different, but they don't tell us what it is. So in a case like this, I want to actually look and see what those effective nuclear charges are. So we can see that sodium has a Zeph of 1 and neon has a Zeph of 8. Instead of calculating, particularly for our main group elements in the S and the P blocks, you can just look at the number of valence electrons, and that's going to tell you what the Zeph is. So Zeph increases from left to right across the table. The sodium valence electron is really only going to feel the attraction of one of those protons in the nucleus, while the outermost electrons for neon are going to feel the attraction of 8 protons. Therefore, the sodium valence electron, not being held as tightly to the nucleus, is easier to remove and requires less energy to remove. Therefore, its ionization energy is lower. Now, as far as the other choices, the reason that melting point, as we take a look back over here at our choices, it said sodium has a higher melting point than neon. Sodium has fewer naturally occurring isotopes, density. Well, melting point isn't a function of Zeph. It's a function of bonding and intermolecular forces. Isotopes depend on the numbers of neutrons, not protons and electrons, which is what makes up Zeph. And density is not a function of nuclear charge either. Temperature, intermolecular forces, bonding, things like that, but not nuclear charge. And since that first statement was all about effective nuclear charge, the only reasonable choice was D. Number 6, what's the average atomic mass of the element represented? Well, we don't know what the element is, but we do know that it has 2 isotopes, 10 and 11. These 2 isotopes are not equally represented or distributed. We can see that 80% of the time you would find the isotope 10, and in a sample of 100 atoms, 19.9% of the time you would find isotope 11. So there's a lot more isotope 10, which means that in a weighted average, which is how we calculate average atomic mass, it should be skewed more towards the number 10 than 11. If they were, and so that means that C is an incorrect answer. For A to be the correct answer, the 2 isotopes would have to be represented at 50-50. Since they're not, B and D are 2 reasonable answers. Let's see why B is the correct answer. We just do the math. So here I've done the math 2 different ways. In the first representation, I've changed the percentages into their decimal equivalents, and down here I've just left the percentages in their original form and divided by 100, which effectively does the same thing mathematically. Question number 7. The average atomic mass of a chlorine atom is 35.45 atomic mass units. Chlorine consists of 2 isotopes, chlorine 35 and chlorine 37. Which of the following most closely approximates the relative abundance of these isotopes? Well, if the average was exactly between 35 and 37 at 36 atomic mass units, we would have a 50-50 split, but we don't. So B is out. Also, because 35.45 is much closer to 35 than it is to 37, it means that the chlorine 35 isotope is represented more often than the 37. So that means that choice A, with only 25% 35, is out. So now we're left with C and D. So how do we make our choice here? Well, let's see the math. To determine it mathematically, we set the percent abundance of isotope 35 at X, and then isotope 37 is at 1 minus X, where that 1 sort of represents that 100%. We solve for X and we get 0.75, and therefore 1 minus X is 0.25. Converting back into percentages, we get 75% and 25%. Question number 8. The first ionization energy of magnesium is 738 kilojoules per mole. A good estimate for the second ionization energy of magnesium is blank. Well, first ionization energy represents the amount of energy required to remove the first valence electron from this atom. As we remove electrons, each successive electron becomes more and more difficult to remove. Essentially, the Zeph increases. Each electron becomes more attracted to the nucleus. So since they're harder to remove, successive ionization energies are greater. So that means that our choice has to be greater than 738, which eliminates choices A and B. So C and D are both reasonable, but well, why is C the best answer? Well, successive ionizations, as I said, always increase, so A and B are wrong. But magnesium has two valence electrons, so the ionization energies should be relatively close to each other while still increasing, and that rules out D, so C is our best estimate. Question number 9. Which of the following is the reason that ionization energy generally increases from left to right across the first period of the periodic table? So this type of question is one that you may find as multiple choice or typically is a free response, open-ended question. The key here is noticing that the word reason is italicized. They're not asking you here to just simply restate what the periodic trend is. They actually even tell you what it is. So restating it isn't going to get you a point. They want to know why. Generally speaking, why in terms of periodic trends is we want to relate that back to Coulombic attraction or Coulomb's law. And in the numerator of Coulomb's law, we see charge is the term, and in the denominator of Coulomb's law, the term is distance. So whenever we're talking about periodic trends across a period, left to right, if we can use Zeph or effective nuclear charge, that numerator from Coulomb's law, we want to use that as our primary argument or reason for that periodic trend. And when we're moving down a group, because we're adding energy shells, we want to use distance from the nucleus or the denominator of Coulomb's law as our reason for that periodic trend. So in this case, since we're moving left to right across a period, we want to talk about Zeph or effective nuclear charge. So what's wrong with A? Well, in A and in B, those are just really restating exactly what the trend is. They're just restating the question. So there'd be no point there if this were a free response question. In C, as the atomic number increases, more electrons are added to the atoms. Well, that's true, and that increases electron-electron repulsions. You might think that that's true, and in some cases it is, but electron-electron repulsion, as far as a reason is concerned, is used primarily when we have paired electrons in the same orbital, and that second electron is actually a little easier to remove than one that's not paired. So we want to really isolate those repulsions as a reason for when we have two electrons paired, one up and one down spin in the same orbital. And that's not really the case here. We're talking about a general trend. So D, as the atomic number increases, more protons in the nucleus cause an increase in the effective nuclear charge. And there's that Zeph, making it harder to remove the electrons. So here I've just explained it again. If you ever want to take a look at this without seeing the video, you can read the explanation without all of this chatter. Number 10, what's the best explanation for the decrease in first ionization energy moving from beryllium to boron? Again, this is one of these things we want an explanation for a trend. Now, ionization energy from beryllium to boron, you would expect going across the period that ionization energy would increase. But here it decreases. So what is that about? Well, this is an example of two elements in the same period. The additional electron, as we move from beryllium to boron, is unpaired. So repulsions are not a preferred explanation. Choice B would cause an increase in ionization energy. And there is some truth to C, but stability is not one of the favored explanations. Remember, we want to use Zeph or we want to use distance. D uses distance from the nucleus as an argument, but that's typically if we're going down a group. So we want to use terms from Coulomb's law whenever possible. So let's take a look back at this. Electron-electron repulsions, we said, are out because we're not dealing with paired electrons in boron. Moving from beryllium to boron, protons in the nucleus attracting valence electrons, that would cause an increase in ionization energy. That's not what the question's talking about. Again, I said there was some truth to C, but this is not an explanation as far as just saying that something is more stable than something else is not what we're looking for in AP chemistry. But indeed, the electrons in beryllium are located in the 2s subshell, which is closer to the nucleus and thus harder to remove than the 2p electrons in boron. And so that is a distance from the nucleus explanation where we're not actually moving down a group, but those 2p electrons are a little further out because they're higher energy and electrons, and they're harder to remove. Sorry, misstated that. They are not harder to remove. The 2p electrons are further from the nucleus. They are easier to remove, and that's why we have a decrease in ionization energy right there. Okay, so let's take a look at number 11. Okay, here in number 11, we have a table that shows the first, second, and third ionization energies for an unknown element. And they want to know if Y is a halogen, which compound will it make with element X? So again, this represents element X. We can see that the first and the second ionization energies are relatively close to each other. There's a gradual increase. And then suddenly there's a very large increase in ionization energy. That means that these first two electrons are valence electrons, and the third electron is a core electron, the next energy level in closer to the nucleus. That's why it's so much harder to remove. So that means this element has two valence electrons, so it's in group 2 and would form a 2+ ion. Y is a halogen, and as we can see here, since Y is a halogen, it makes a 1- ion, and therefore it will form the XY2 compound to have a balanced charge, +2, and then 2 -1 charges. Number 12, the reactivity of the alkali metals increases going down the group. So that's just a statement they're making. Which is the correct explanation for this trend? So again, we're going down a group. And what happens as we go down a group? Well, we add energy levels, okay? And as we add energy levels, the valence electrons, which are the ones that for alkali metals are going to come off to form positive ions, those valence electrons get farther and farther from the nucleus because they're increasing numbers of shells. Since they're easier to remove, that makes the ionization energy decrease. So it requires less energy to remove those valence electrons. Notice B talks about greater nuclear charge as you remove down the group, but effective nuclear charge doesn't. Effective nuclear charge stays the same. As far as nuclear stability in C is concerned, nuclear stability has, exactly like they say right here, has to do with whether you have a radioactive isotope or not, and it really has nothing to do with reactivity, which has to do with adding or removing electrons. Also, the greater mass as you move down a group, well, yes, atoms do have greater mass, but that's not going to cause an increase in kinetic energy. Temperature is going to cause an increase in kinetic energy. So therefore, again, remember that if you're going down a group, you want to think about how those energy levels are added, and the atoms, their atomic radii are getting larger and larger, and the electrons on the outer shell are further from the nucleus, and therefore they're going to be easier to remove, making the ionization energy go down, or decrease, I should say. Number 13, in which of the following electron transitions for a hydrogen atom does the light emitted have the longest wavelength? Okay, so longest wavelength means it's going to be the lowest frequency, and it's going to have low energy. Long waves are low energy waves. So if we take a look at the Bohr model of the atom, you can see here that we've got our energy level 1, energy levels 2, 3, 4, 5, and 6. The energy that is given off when a photon is emitted depends on how close together these energy levels are. If the energy levels are very close together, the energy difference is small and we have low energy. If the distance between the two energy levels is large because we've got multiple jumps, or like between 2 and 1, if that electron falls back down to a lower energy level, it's a big distance, then we have high energy or higher energy photons. So let's go back to those questions, or to the possible answers. You can see from 5 to 2, that's a jump of 3 energy levels. And then from 3 to 1 is a change of 2 energy levels. So those are probably not going to be it. We're going to have higher energy. 4 to 3 and 2 to 1 are both reasonable because they're only changes from one energy level to the one right next to it. But again, as we see here in the Bohr model, from 4 to 3, those two levels are pretty close to each other. So that's a relatively small energy difference. But 2 to 1 is a much larger distance, and therefore that correlates in our model to a larger energy. So that's why the 4 to 3 transition emits the lowest energy photon. Number 14. Nitrogen's electronegativity value is between those of phosphorus and oxygen. Again, that's a statement they're just making. It's true. Which of the following correctly describes the relationship between these three values? So what you have to think about electronegativity, look at where nitrogen, oxygen, and phosphorus are on the periodic table. Nitrogen and oxygen are in the same period, left to right. And oxygen is closer to fluorine, so it's going to have a higher electronegativity. Phosphorus, on the other hand, is lower on the periodic table. It's right below nitrogen. And if nitrogen is between these two, it must mean that oxygen has greater electronegativity and phosphorus has the lowest electronegativity. So we have to pick one of the choices that puts oxygen with the greater electronegativity and nitrogen there in the middle. So you can see A and B doesn't do that. So both of those statements are false. In C, it says that nitrogen is smaller than oxygen. It's not really smaller. Its radius is actually a little bit larger. And it's a little less, but it is less massive, but that mass change is not going to be affecting its electronegativity. Nitrogen does have fewer electrons than phosphorus. So there are some things that are a little bit true in these statements, but you have to look at this statement overall and see does it make sense. So think about what the definition of electronegativity in C, and you'll see that C is not the correct choice. For D, everything there is true, so that is our best choice, and that's why we chose D as the correct answer for number 14. Number 15. The first ionization energy for a neutral atom of chlorine is 1.25 megajoules per mole, and the first ionization energy for a neutral atom of argon is 1.52 megajoules per mole. How would the first ionization energy value for a neutral atom of potassium compare to those values? So again, let's take a look and see where chlorine and argon are on the periodic table. Chlorine and argon are in the same period right next to each other. Chlorine is in group 17 and argon is in group 18, and so therefore that increase in first ionization energy is what we expect. But where's potassium? Well, it's right after argon at the beginning of period 4. Now, because it's in group 1, potassium has one valence electron, and so we would think that it would be much easier to remove than the 7 or 8 valence electrons for chlorine and argon respectively. So I would expect for potassium to have a lower first ionization energy than both chlorine or argon. And again, you can see my explanation of the false and then finally the true answer here, as I just stated before. For number 16, neutral atoms of chlorine are bombarded by high energy photons, causing the ejection of electrons from the various filled subshells. Electrons originally from which subshell would have the highest velocity after being ejected. Okay, so the first thing that I think of here is that the ones with the highest velocity are going to be the ones that have the highest energy. And so when I look at my choices, I might be tempted to say that 3D have the highest energy. Those are my highest energy electrons, therefore they have the highest velocity. But they're trying to trick you here, because chlorine, take a look at where it is on the periodic table in period 3, doesn't have any 3D electrons. So the highest energy electrons that chlorine does have are 3p, and that is our correct answer. Number 17. A photoelectron spectrum for which of the following atoms would show peaks at exactly 3 different binding energies? Well, in PES, or photoelectron spectroscopy, individual peaks show up at different sublevels. By sublevel, I mean 1s is a sublevel, 2s is a sublevel, but 2p is a different sublevel. Then 3s, 3p, 4s, 3d, etc. Each of those are sublevels, and each of those sublevels has its own separate peak. The height of the peak tells you how many electrons are in it relative to other peaks. But here they want to know if which of these elements would just have 3 peaks or different binding energies. So let's take a look at their electron configurations. If we look at those, we can see beryllium 1s2, 2s2, there's only 2 sublevels here. So we'd only have 2 peaks. Neon, 3 sublevels, 3 peaks. Sodium, 4 sublevels, 4 peaks. And aluminum at 5 sublevels would have 5 peaks. So therefore we can see that they want to know which one has exactly 3 different binding energies. That's neon, based on its electron configuration. Because remember, the PES, or photoelectron spectrum, is the physical evidence of these electron configurations. Number 18. Which element would have a photoelectron spectrum in which the peak representing electrons with the lowest ionization energy would be 3 times higher than all other peaks? So there's a lot in this one, but just like in number 17, what I'm going to do is take all of these elements and I'm going to look at their electron configurations. Okay, so first of all, I've written the electron configurations for all 4 elements here. Now I'm going to analyze them according to the question. It says they want to know about the lowest ionization energy peak. Well, that's going to be the energy peak that's farthest from the nucleus, because those electrons are the easiest to remove. When we look at carbon, we can see each one of these sublevels has only 2 electrons in it, so all peaks will be the same size. So that's not the answer. Here, the lowest energy peak, is the 2p3, is only 50% larger than the other peaks, so that's not quite big enough. For neon, the lowest ionization energy peak is the 2p6, and 6 is 3 times more than 2, which is how many we have in the other peaks. So there's our correct answer. You can see sulfur is not the correct answer because the lowest energy peak, 3p4, that's only 2 times larger than the peaks that have 2 electrons in it represented, and it is 50% smaller than the 2p6 peak, so that one is out. Number 19. Which of the following represents the first electron affinity of chlorine? Well, we need to go back to what our definition of electron affinity is. Electron affinity is the amount of energy change when an electron is added to an element and to one atom of that element. And so you can see that C can't be correct because we're actually losing an electron here. And here they show adding an electron to an ion that already exists and getting the same thing. This just doesn't make any sense. We're going to start with a neutral atom and add an electron to form this ion in its gaseous state. D is incorrect because it's not one atom. Again, it's the definition of electron affinity that we need to keep in mind here, and it's for adding an electron to an atom in its gaseous state. This energy change, by the way, can be endo or exothermic. It depends on the type of atom that you're looking at. Okay. Number 20. Which of the elements above has the smallest ionic radius for its most commonly found ion? So first of all, let's take a look. We've got oxygen here, a non-metal, and then lanthanum, rubidium, and magnesium. These are all metals. Well, oxygen is going to form its most common ion is an anion, and anions are actually larger than their parent atoms and also larger than um, metal cations. So we're going to take that one out. Lanthanum's a metal in period 6. It's got 6 energy shells, and it's probably just going to lose a couple of electrons, maybe make a 2 plus. We don't really see lanthanum in its ionic form often, but because it's such a big element, even if it loses those electrons, it's still got 5 energy shells. It's really big. Same thing with rubidium. But in the case of magnesium, it's in period 3, so it has fewer energy shells, and its radius is going to be smaller. So that's going to be our answer to our question number 20. Number 21. Which of the following represents an atom that's chemically unreactive? Well, there's 2 reasons why C is the correct answer. I can recognize this as a noble gas because its S and its P sublevels are completely filled, and that's the case for all noble gases, which we know to be chemically unreactive. Why are they unreactive? Well, because all of their electrons are already paired in their orbitals. They don't have any place for bonding to occur. There's no empty spaces, no unpaired electrons. And so, therefore, we've got a really unreactive element here. This right here also represents an element that doesn't have any unpaired electrons, but this 1s2, 2s2, this is beryllium, and compared to a noble gas, this noble gas is going to be the least reactive of them all. 22, representing an atom in an excited state. Well, atoms in their excited states have empty lower energy levels. And you can see right here that this 1s electron, this would be like a hydrogen atom with 1 electron, has absorbed energy, and the electron has been excited into the 2s orbital space. Whereas in the other cases, everything below any unpaired electrons, all lower energy levels are filled. Therefore, these are all ground states. 23 represents an atom that has 4 valence electrons. Well, valence electrons are always in the S and P sublevels. So let's take a look at those S and P sublevels for valence electrons. Here I've got 2 valence electrons. Here, 1, 2, 3, 4. There's our answer. Notice how many valence electrons we have here in your highest level S and Ps. We've got 8 of them. And then here we've got, what's my highest level? Right there. These are my valence electrons at only 2. Number 24. Again, analyzing our electron configurations in our orbital notation, which you should expect to have to draw these at some point, represents an atom of a transition metal. Well, the transition metals are in the D block, so we're going to be seeing D sublevel electrons, and this is the only place that we do, so D is our correct answer. 25. Which of the following ions has the same number of electrons as the bromide ion? Well, I need to look and see how many does bromide have. So bromide, originally bromine has 35 electrons, but since this is an anion, we add an electron to make 36. And so I've calculated based on the total number of electrons or a neutral atom, and then either subtracting or adding electrons to that to create these ions. We can see that the only one with 36 is the strontium ion. 26. Which of the following best helps to account for the fact that the fluoride ion is smaller than the oxide ion? Okay, again, I want to caution you, a lot of times in these questions, they make a statement, and you need to make sure that you don't try to refute that statement. They're not asking you if fluoride is smaller, they're saying it is, but they want to know why. Okay, so nuclear mass, well, A is just not true because fluoride does not have a larger nuclear mass. It is more electronegative, but that isn't going to affect radius, which is when they say smaller, that's what they're talking about. Neither is polarizability. So again, since we're talking about a periodic trend, we're really talking about radius here. We want to talk about something that has to do with Coulombic attraction. So we want to look at, in the same period, Zeph, or effective nuclear charge, is going to be our explanation of choice for these kinds of trends, and that's what we have here in B. It does have a larger nuclear charge than oxygen, and that means it has a greater effective nuclear charge, and that pulls the electron cloud in, making the fluoride ions smaller. Which electronic configuration represents atoms of the element having the highest second ionization energy? Now, atoms with relatively large second ionization energies have only one valence electron. That first electron is easy to remove. But once that outer shell is gone, now you're going to be removing electrons from one of your core levels closer to the nucleus, and so we have a really big increase from first to second ionization energy. So when we go back and look at our choices, where do I see an element that has only one valence electron? And we have it right here in choice C. Number 28. What wavelength corresponds to a frequency of 8.22 times 10 to the 9th hertz? So let's remember what a hertz is. It is an inverse second. That's frequency represented by the Greek letter nu that kind of looks like a little V. And remember, your equation sheet that you get with your AP exam is going to have these light equations, C equals lambda nu and E equals H nu, are going to be there. And they're also going to provide you in the right-hand column of that sheet with the constants you need. So this is really just a plug and chug kind of calculation right here, where we see lambda, which is wavelength, is equal to c, the speed of light, divided by the frequency given in the problem. This is the speed of light that's given in the AP equations and constants table, and then divide that by the frequency, and in hertz, which is an inverse second, and the inverse seconds cancel, because it's a division, cancel with these seconds, leaving us in meters for our wavelength. That's an important thing also to remember, that if you're given wavelength in nanometers frequently, you cannot plug nanometers into this equation for wavelength before you change it into meters. It must be in meters so that we've got unit agreement. So keep that in mind for future calculations. Number 29, the electron configuration, ending in 3p6, represents all of the following except which one? So again, you've really got to go and analyze every single one of them and see which one it doesn't fit with. When we get down to V at the end, we see the vanadium atom, its electron configuration. See that right here. And so the 3 plus ion has 3 electrons removed. And therefore, we're going to remove those 4 s2 electrons and then one here. We're going to end up with a 3d2 at the end of that, which is not what they say here, okay, at 3p6, but the other ones do. So unfortunately, you kind of have to work through all of these, or at least be really good at figuring out what's going on with electron configuration changes for ions in the periodic table. And finally, number 30, the lines in the emission spectrum of hydrogen result from what? Well, an emission spectrum, and particularly the one that we're familiar with, that we talk about, that Bohr used to come up with the Bohr model of the hydrogen atom, we look at the visible spectrum. We think of that as light. Well, how is light formed? And light is formed when an electron has been excited into a higher energy level, and when it drops back down to a lower energy level, that energy difference is given off in the form of a photon of light. So you think about how light is made in this particular case. Um, so that's what I'm saying here. Light is produced by electrons transitioning. Removing electrons like in A, that makes ions. It doesn't create light. When they talk about decomposing atoms, that seems to indicate probably radioactive decay when we think of a decomposing atom. And this is a nuclear change. That also does not produce light. So we're looking for something that makes light, hence this emission spectrum. Electrons given off by hydrogen when it burns. This is not when we think about when we do flame tests. This is not really giving us the full emission spectrum. Um, we really want more of a definition of why this is happening at an atomic level. So in all of these questions, especially the ones that talk about reasons why or explaining why we're looking at a particular periodic trend, again, keep in mind that you're looking in your responses to free response questions to something like the answers in these multiple choice questions. You want to confine your arguments or your explanations to talking about the terms in Coulomb's law. You want to talk about charge if you're moving across a period, and by that I mean by effective nuclear charge, increasing left to right, and what that does to your periodic trend. And then periodic trends down a group, you want to focus primarily on distance, which is in the denominator of the Coulomb's law, and you want to talk about that because as you go down the group, um, you're adding energy levels, and so your valence electrons are getting farther and farther from the nucleus, and how does that affect the particular trend that you're talking about? So also make sure that you look at these questions. They are also found, these are the practice questions, not in PowerPoint form. So there are several different ways that you can use these in the classroom.